independent samples. In other words, the samples cannot have anything in common. Last time I wrote that there is a disadvantage to this method in the sense that one, the population variances or standard deviation are known and are almost identical. If they're not almost identical, then that's a problem. But even if we put that aside, in practice, we do not know the population variance in most cases. So that is an issue as well. So I want you to give me an example of two independent samples. The lectures are available online now that we have this camera. Did we look at it? No? Wow. Did anyone watch it? Okay then. You know it is helpful. Regardless, the videos are posted in Canvas modules. So if you want, you can go and look at the videos. So an example for two independent samples. Something I can collect data from here.
Last time we did sophomores and juniors' ages.
Right, we have to do something different. Go ahead.
You can do shoe size and color your background.
Shoe size what?
Do shoe size and height. Do that.
Of an individual?
Okay.
So if we pick the shoe size and height of the same individual, they are sort of dependent. Do you agree?
I mean, maybe it's somewhat.
Huh?
Yeah.
There is some relation. We do not know. We want it to be completely independent of each other. So the two samples should not have any sort of overlap.
So like height and major.
Height and major. So major is not numerical, right? We want numerical samples.
Height and number of siblings.
Height and number of siblings. Okay, they are independent, but should we compare the heights of people to the number of siblings they have?
I don't know, you wanted two independent.
So last time we looked at the ages of sophomores versus juniors. Juniors. So that is, the average age is important. We have two independent samples. It would make sense to compare those two. So
Why not shoe size between men and women?
shoe size between men and women, right? So that would be a good example. I don't have enough males here, so let's try something else. How about 4 people? How many of you have had pets here? Okay, dogs? Cats? Wow. How many of you have had pets that have died. Okay. How many of those pets were male? Still a very small sample. Well, for the sake of it, let's just do it. So we are going to compare male dogs and female dogs. Let us assume that the population variances are identical, almost identical, because if we don't make that assumption, then we can't use pooled variance. So, let's see. Now we could have gone with the shoe sizes example also. So, who said they had dogs that died? Okay, start with you, Jessica. Male or female?
Oh, female. She was 15.
Okay.
Female, I think she was 13.
Did you have a dog? No.
Male, he's 12.
Go ahead.
Female, she was 13.
How much?
13.
13.
Female, she was 12. I've had both male and female.
Okay. Did both of them die?
Yeah.
Okay.
The 13 female and 14 male. 8.
8.
Male, 15.
Right now, Laura,
13 female.
female. Male 15.
Who's male, 11.
Okay. Not bad. Now keep in mind, in practice though, we need a bigger sample, but just to illustrate, we can use this small sample because all I want to do is explain the method. from last time, if the confidence level is 95%, what is the value of alpha?
0.05.
0.05. Great. We need to find sample statistics. So the first one, the book probably uses mu1 and mu2. I like to use subscripts that correspond to the problem so that we understand it better. So mu sub m would be the average age when a male dog dies, and mu sub f would be the average age when a female dog dies. Now that we have two independent samples, we'd like to make use of the sample and find the sample mean, the sample standard deviation, and the number of observations. So you all know how to use one variable statistics. Go ahead and use one variable statistics for each of those samples and tell me what the mean, standard deviation, and sample size are. We will call male as sample 1, female as sample 2. What is the sample average for males?
12.33.
Huh?
12.33.
12.33. Is she right? Yes. Standard deviation?
2.658.
2.658. Did we get the same? For females?
13.8.
13.33.
33.
And for standard deviation?
1.033.
1.033. We'll just call it 3. So that information comes from the sample. We want to use the pooled standard deviation or pooled variance. So I'm using this formula because that is conventional, but do keep in mind N1 corresponds to male, the number of observation from the male group, and N2 is for female. Good? So we know the value of N1, N2, we know the standard deviations. So if we plug that in, so I'm just plugging in the numbers and tell me what you get. Do we have have an answer? What do we get?
I got 35.908.
35.
I got 40.26.
Did we divide by 10?
I got 4.07.
4.07. Don't forget that 10. There is 10 in the denominator. That sounds believable. Where did we go wrong? Did we just forget to divide by 10?
I did it 3 times, I don't know.
I didn't get that either.
This seems right to me. So first evaluate that and make sure you put parentheses. So evaluate the numerator, get an answer, then you divide by 10.
I got the same one.
I got 2.
Okay, so don't be in a rush. I've put all these parentheses for a reason, because if you did it this way, you would not be making mistakes, and do not forget to divide it by 10. In the calculator, if you just keep on typing this and then put divide by 10, that is incorrect.
Yeah, I got that.
Yeah. So we have 4.07. So if the variance is 4.07, what is the standard deviation? You can guess easily, it's 2.03.
2.02.
2. One of the ways to easily recognize if the answer that you have is correct is to compare this value to the 2 standard deviations that we have over there. The answer that you get has to lie between these 2 numbers. So does 2.02 lie between the 2 sample standard deviations? Yes. So you did everything right. So if you thought the answer was 40, 40 clearly doesn't lie between 1.03 and 2.66. Yes?
If you were to put all of the data points into one list, would you get that 2.02 for your standard deviation on that list?
No.
Okay, so it's not the same.
Good question though, but in order to find an interval, we need to know the margin of error. Last time I mentioned that the margin of error is always the product of 2 things. What are the 2 things? You've got to read, people. Critical value and
Standard error.
standard error. The standard error in this case is simply the standard deviation, the pooled standard deviation, multiplied by the square root of 1 over n1 plus 1 over n2. N1 is nothing but the number of observations in the first sample, which is nailed. N2 would be the number of observations in the second sample, which would be the female results. So put that in and tell me what you get. What do we get? 1.07. point, no, point,
I got 1.16.
oh, that's fair. 6. So that is the standard error. And where do we get the critical value from? We obtain the critical value using a distribution. And in this case, the distribution is T. What was the degrees of freedom last time? When we did the case without the pooled variance, we used degrees of freedom, and what was that value? Huh? 11. No, last time.
7 minus 1, 35.
It's just n minus 1. We have two samples here.
Oh,
You can look at the notes. So, okay, let's just say n minus 1, which would, in this case, it is 5 and 5, doesn't matter. What if we have n minus 1 and n here is 17, n there is 22, which one would you pick?
Won't you use
The smallest.
the minimum?
Would I? Should I?
oh yeah.
Yes. We use the minimum of the n minus 1s for each of the samples. But anytime we have pooled variance, we simply use that denominator over there in the pooled variance, n1 plus n2 minus 2, which would be 10. What function in the calculator do we employ to find the critical value from a t distribution? Inverse t, very good. So the critical value here which we know is simply the area under the curve below the positive critical value. You may wonder, well, what curve is he talking about? So that is the positive critical value, because the 0 is going to be right in the middle. So we want to find the area below the positive critical value. If the area above is alpha over 2, the area below is 1 minus alpha over 2. And we can just use the function inverse t. 0.975, comma 10. What do? We do not have the inverse t function. in your calculator.
Is the chart?
Use the chart. Okay, put it in the calculator and tell me what you get. So we have the margin of error, which is the product of the critical value and the standard error. So E, which is the margin of error, is equal to the standard error, which is 1.16, multiplied by 2.23. And what do we get when we multiply those two? Two point
2.59,
55.
59.
What is the difference in sample means? So we have the sample mean for males, we have the sample mean for females. Tell me the difference once you're done writing. Do you have the difference? You know you can use the calculator to tell me.
-1.
-1, exactly. Is it exactly -1?
Yeah.
I erased it, so I don't know. So -1 minus 2.59, less than the difference in means for the average age when a male dog dies, minus the average age when a female dog dies, and we have -1 plus 2.59. Good. And that is the 95% confidence interval for the difference in the average ages of when a male dog dies and when a female dog dies. And here is the question. Do you think the average age when a male dog dies is statistically the same as the average age when a female dog dies? We went over this last time on how to make inference using the confidence interval that we obtain for the difference in means.
No, because, when you subtract U1 and U2, you get a negative number. It means that the average age for a male dog just is less than female.
Okay, good way of thinking, but they're only looking at that. What about this? That's a positive number. Is that the case that if you're an optimist, you pick this and be satisfied? If you're a pessimist, you pick that and be satisfied? Do you see my question? So, Lauren suggested, okay, we have a negative number, which means the average age when a female dog dies has to be bigger than average age when a male dog dies. But that doesn't apply here because I have a difference that is positive also. So it's neither that nor that, so what can we conclude? Could they be statistically the same? Yes. We're not saying that they are exactly the same. We're saying that statistically, we can't say that there is a significant difference. An easier way to identify that is 0 falls in the obtained interval. So 0 falls clearly between negative 3.59 and 1.59, so statistically they are likely to be the same. Are we clear? Yes? Okay, if you have your calculator, go ahead and grab that. So what I'm going to do is I'm going to enter the data in list 1 and list 2. Erase the data and I write the data. Thank you. So I entered list 1 as well as list 2. The data is in there. Exit. Press start. go over to tests. Scroll down. It says 2 sample Z interval, 2 sample T interval. Which one should we use? T. And since we have the data, I'll just leave it as is, where the cursor is at. The confidence level is 0.95, and it is asking you whether it should be pulled or not. What did we do? Did we pull it? Yes. So switch it over. I had one job. And hit calculate. So what answer do we get?
Same.
The same thing. So what I'm going to do now is I'm going to go back. Are we clear with this? Did we have issues? Yes?
I have a question about the pool. Why was it yes?
Because we pulled the variance when we first started. Right, SB, we combined the two to get pulled variance.
So will it always be yes?
No.
Okay.
The last time we did not pull the variance.
Okay.
So start, if we go over to tests and I'm going to select no. So this goes back to what we did last time, the session before the exam. Remember we did square root of s1 squared over n1 plus s2 squared over n2, and we picked the degrees of freedom to be the minimum of n1 minus 1 and n2 minus 1. And if I don't pull, that would be the answer. So what is the sample size? The sample size n1 is 6, n2 is 6. And if we have to use the process that we did previously, the degrees of freedom should be n1 minus 1, the minimum of n1 minus 1, and n2 minus 1, correct? n1 here is 6. N2 is 6. 6 minus 1 would be 5. Yet, do we see 5 for degrees of freedom? What do we see? We see 6.475. So, why do we have this difference? After a bit of research, people found out that using the minimum of n1 minus 1 and n2 minus 1 is not the most accurate way to obtain an interval. So, a guy named Welch what is the degrees of freedom that we had? 6.47 something? Yes? Is unpulled a word? So Welch's method simply estimates the degrees of freedom. And it's a huge formula. You don't have to memorize the formula. All you have to do is put it in your cheat sheet. So don't memorize this. I know this because of the theory behind it. Looks very painful. So what was the standard deviation for the male sample?
2.66.
2.66. And N1 is 6. For the female sample it was
1.03.
1.03. Don't even think about typing everything at once in your calculator. This is what you should do. First find that bit, then you find that bit, write it down. Maybe you call that value as A, call that value as B. Then write it over here. If you calculate it as A and B, it would simply reduce to A plus B squared divided by A squared over 5 plus B squared over 5. And still, evaluate the numerator first, then the denominator, then divide the two. What is the value of A? Just this time. 2.66 squared divided by 6. I'm calling it A and B so that you don't make any mistakes.
.08. Oh, hold on, that's why. So 1.18.
This?
2.66 squared divided by 6.
Uh-huh.
Yeah, I got 1.18.
Yeah, me too. 1.1.
B.
.177.
0.18. Okay. What is A plus B squared? 1.36 squared. One point seven
1.84.
eight.
I got 1.5.
Oh, 1.5.
8.5.
8. Okay. And the denominator part we have a squared over 5 plus b squared over 5, which would be 1.18 squared over 5 plus 0.18 squared over 5. And what is that?
128 plus.
Oh, 0.28
Yeah.
two plus.
.006.
Well, it is simply, 0.286. Yes. Now we take that number, divide by that number to get the degrees of freedom. And what do we get? 6.47. Now go back to the interval that we did and check it as not pooled. And if you look at the DF, that DF would be 6.47. Yes? We just did. So the key here is what we did last time when we did not pool, we actually used the minimum of the two DFs, which is N1 minus 1 and N2 minus 1. Even though that is acceptable in some cases, this is more accurate, and this is what we call the Welch's method. What changes is the degrees of freedom, but keep in mind, if the degrees of freedom changes, the critical value would change. If the critical value changes, the margin of error would change. The margin of error changes, the interval would change. Does that make sense? So given the choice between the pooled case, the not pooled case, and not pooled Welch's case, the most accurate would be not pooled Welch's. Good? So in terms of the best interval, good. Earlier I mentioned why the pooled is not the best thing to do, because we've got to know the population variance, which is not very practical, and not only that, those variances have to be identical. unpulled that we did last time, it is acceptable, but it's not the most accurate. The same approach, instead of using the DF that we used last time, if we use the DF that we have here, this is going to be the most accurate. With me? So very subtle differences. Are we clear? Good. So the calculator could do that and that. That part the calculator cannot do. Good. So in the calculator, if you set rule to be yes, you get that. If you say no, it is going to do that. But the one that we started with last time is that case, and the calculator cannot do that. The reason why I wrote this formula is because I'm quite sure there might be some questions in the homework where we give you the standard deviation for the first and the second sample, the sample size for the first and the second sample, and say, hey, what is Welch's DF? So you should know this formula. Good? Okay. Before we end talking about subtle differences,
I have a question.
yes,
Is it still 10.1?
yes.
Okay, thank you.
So if we know the population variance is sigma 1 squared and sigma 2 squared, then in the formulas that we discussed, we simply replace S1 squared, S2 squared, but whatever value we know. Instead of a t-distribution, we use a standard normal distribution, which is nearly a normal distribution with zero mean and standard deviation 1. A standard normal distribution does not depend on the degrees of freedom. What function do we use to find a critical value from a standard normal? Earlier today we used inverse t, inverse normal. The formulas would remain the same, but we simply use inverse normal. Good. I want you to save the data from today. Before I start 10.2, I'll show you what function to use in your calculator to achieve this. Good? Okay, if you have questions, talk to me. If not, I will see you next time.